Welcome everybody to the Algebra 2 Chapter 3 review. We didn't have a lot of concepts this chapter, but quite a few of those are pretty involved. So this test will be something that we definitely don't want to sit and stare at a problem for very long. So if you're watching this video, you're taking the right steps and preparing yourself. I'm going to go through and show how we can do pretty much everything without a calculator, but there are a couple that ask for answers rounded to the nearest hundredth or something like that. So I will show how to use the calculator for those problems as well when we get to the end. So without further ado, let's get started. Okay, the test opens up, or our review opens up, I should say, with two solve by graphing problems. And since chapter 2 was primarily focused on graphing quadratics, we should have a pretty strong understanding of how to graph those quickly. So for the first one, I do notice that it's not set as like y equals right away. And really, when we're going and solving quadratics, we said that we really want to make an effort to get that set equal to 0 first. So my first move is going to be subtract 4x and subtract 5 from both sides to get that quadratic set equal to 0. Then, to graph it quickly, I'm going to use x equals negative b over 2a to find the axis of symmetry. In this case, that is negative 4 over 2 times 1, so x equals 2 is my axis of symmetry. If I plug that x equals 2 into the original equation up above, just looking at the left-hand side, I will find my vertex. So I get 2 squared minus 4 times 2 minus 5. That gives me a y-coordinate of my vertex of negative 9. And from there, it's opening upward, and it's not stretched or shrunk at all. You can see it's a lead coefficient of positive 1. So that means it's going to follow our standard parabolic growth. And we practice this in chapter 2. There's a video on this on the haiku page as well, or in my YouTube channel if you're not from Hananiga High School. But we're able to use that to graph the function very quickly. You could also type this right here in as y equals in your calculator and output a table of values to get this graph plotted very quickly as well. The solutions here are where the graph crosses the x-axis, right? I want to find out where that function has 0 height. And those two places are x equaling negative 1 and positive 5. For the second one, I'm going to treat this one similarly. I notice, though, that this one's going to open downward. Let me switch colors for this problem. But it's already set equal to 0, so my x equals negative b over 2 times a also gives me x equals 2 for an axis of symmetry. And if I plug in that 2 into this equation, I get negative 2 squared plus 4 times 2 minus 1. That gives me a y-coordinate of 3. So there's my vertex, and I can follow again standard parabolic growth because it's not stretched. I could also use a calculator table if I chose. But I get this graph, and we see something interesting. I'll notice that I do not have clean crossings. If that is the case, all is not lost. By graphing, the best we can do is say it crosses somewhere between 0 and 1 on the x-axis, and somewhere between, it looks like 3 and 4. And that's as close as we can say from the graph. It does have crossings there, but we would have to employ some other methods if we wanted to find those exact values. All right, in the next section, solve by factoring. This is something that we should have well practiced from Algebra 1. We still want to get our equation set equal to 0. So I've got 3n squared minus 75n equals 0. I definitely don't want to divide both sides by 3n. I am losing a solution there for sure. When I have two terms like this, and they're both variable terms, I'm able to take a greatest common factor. So in this case, 3n, and I'm left with n minus 25. So my solutions are n equals 0 from that loose factor of n out front, and n equals positive 25, because that's what would zero out this factor that we had as well. For problem number 4, here again, let's get it set equal to 0. 6t squared, I'm going to add over 15t. and I'm going to add over 12 to get that set equal to 0 first. And we do have a leading coefficient that is not 1, and I am unable to take a greatest common factor. I can't divide both sides by a number and have it come out cleanly. So we have to take the product of the first times the last, and we get 72. And I'm thinking, what numbers multiply to be 72 and add up to 17? Oh, it's 8 and 9. So now what we're going to do is we're going to set up our factors to make that foiling process work for this trinomial that we have the arrow pointing to right here. Well, I know I'm going to have a t times t to make my t squared term. First times first makes that 6t squared. And I just want to think, how can I set this up using these two numbers to make that happen? And what we do have an algorithm that says, oh, you just divide 8 and 9, you divide them each by 6, and you get those nice little fractions that turn into the factors. And that works really well. But what will ultimately be faster is to think, how can I take a factor of this 6, and it takes some practice to really appreciate this, and a factor of 12, and multiply together to get one of these two. So I usually take the number that has fewer factors, in this case 9, and say, okay, how can I grab something from this 6 and something from this 12 to multiply together to give me 9? And I can see pretty quickly that I can take 3 times 3 and do that. So I know that my outside product is going to be made by that 3 times 3. Right? These numbers, this 8 and 9, those are really my outer and inner values from FOIL. Once I have that set up, then I can just say, oh, first times first has to be first. So 3t times something t has to give me 6t squared. This must be a 2. Last times last has to produce a 12. This must be a 4. And in order to make that a positive 9, to make my last times last a positive 12, those are my factors. So that is the fastest way that I've found to factor these out. And because it does say to solve by factoring, I need to see this factored step. All right, grabbing the solutions out of those factors is pretty easy. We have to switch the sign, obviously, when we take them out. What if this were 3t plus 4 equals 0? Well, I would subtract the 4 and divide by 3. Here I would subtract the 3 and divide by 2 out of my second factor. So those are my solutions for that problem. You are more than welcome to use the algorithm that you may have learned freshman year or practiced in geometry. I just wanted to introduce this a little faster method of factoring. And we'll see it again here in number 5. Start by getting it set equal to 0. That means adding 35 to both sides. Again, I can't take a GCF. 4 times 35 is 140. And after a little bit of searching, I find that to make that negative 33x, I need negative 28 and negative 5. Okay, so let's set up our factors. We've got something x and something x, making that 4x squared. I'm definitely going to try and make this negative 5 happen first with my outside product, because I can take a 1 from this 4 and a 5 from this 35 to make that happen. So I've got 1x and negative 5 to produce that negative 5. Then first times first, 1x times, oh, that has to be 4x to make my 4x squared. Last times last, this has to be a negative 7 to make that positive 35, and we've got our factors. Our solution set then, x equals a positive 7 or a positive 5 over 4. And lastly, problem number 6, it's already set equal to 0. This is a difference of squares, so it should be very fast for us to factor that out and find our solutions, x equals 1 or negative 1. Now I'm using the squiggly little braces to contain my solutions because we have more than one. It's technically a set of solutions. That is not necessary. However, that is good practice mathematically. That's a nice way to denote when you have more than one solution. All right, for number 7, we've got an area of the triangle problem. On the test, this area formula will be given, but coming out of geometry, we should be automatic with 1/2 times the base times the height. I know the area is 42. I'll substitute that in. I know my base is 2x plus 8, and I know my height is x plus 3. Then to make this easier to work with, I'm going to distribute this 1/2 into the first factor. It doesn't distribute to everything there because it's three things multiplied together. 1/2 times the first, and then all of that times the second. So I can make a much easier trinomial by distributing this 1/2. The 2x plus 8 just gets cut in half, and then the x plus 3 is unchanged. All right. Well, if it's we can see that when we FOIL this together, we're going to get a trinomial, and I mean we should expect that. The whole chapter was on quadratics. So we get x squared plus 7x plus 12 when we FOIL those together, and that's still equal to 42. Let's subtract over the 42 to get it set equal to 0. And then this one is a nice, easy factoring problem. We get plus 10 and minus 3 for our magic numbers there to produce our factors of that new quadratic. And the solutions that come out are x equals -10 or x equals +3. Now there is a stipulation here. Because we're trying to work with a real triangle, a geometric construction, I can't pull out a tape measure and say, okay, let's make this -10 inches. That will not produce measurements that will construct a real triangle. So the only acceptable solution for this one is x equals 3. We may plug in the numbers into the diagram and check and make sure that that triangle does in fact have an area of 42, just to be sure. This next section, hopefully we are able to fly through this. The big thing that we need to remember for complex numbers is, first of all, our answers need to be the form a plus or minus bi. And then secondly, we cannot end up with an I squared term. So remember that whenever I squared comes up in our problems, that just means a -1. So we're able to simplify that. We called some of these bluegill problems as we were going through. The first thing we want to do is recognize that these negatives under square roots are in fact imaginary terms. So I'd call that I root 52. And then I could go through a factor tree to break apart that 52. It certainly does look like it simplifies. I could divide it by 2 and get 26. Oh, and then I could divide that by 2 and get 13. 13's prime, and then hidden here is 2 times 2. Well, that's 2 squared. That means I get to free a 2 from under the square root. So final answer is 2i, and then that square root 13. 13 just being prime without a matching factor, it does not leave the square root. For number 9, again, let's recognize that we have an I term. And then square root 50, that's 5 times 10 and 5 times 2. So we can free a 5 to join the one that's already out there, but there's going to be a 2 left underneath. So out front, I've got 5 times the 5 that was already there, times I, times the square root 2 left underneath. 25i root 2 should be our final answer. We should be able to really pick up the pace when we get to this section, I hope. For number 10, here we start working with numbers that are already complex, and the temptation here is we see parentheses to try and FOIL, but no, we have two complex numbers and we are simply subtracting them. So I just want to combine the like terms. Maybe I will distribute that negative to make sure I don't forget to apply that negative to everything in that second complex number. But then we're just combining like terms. A 3 and a -8 make my real part of -5. -6i plus 2i is -4i for the complex part, or the imaginary part of that complex number. For number 11, this one, just as it looks, it's distributive property. 3i times 2 is 6i. 3i times -4i is -12i squared. Don't forget that we're doing I times I as we distribute there. And since I squared is -1, this is like -12 times -1. It's really just a +12. So in A plus BI format, I've got 12 plus 6i for that complex answer. For number 12, multiplying two complex numbers, here we're obeying the FOIL method here. 3 times 7 is 21. My outside, I get -9i. Inside, I get +7i. Last times last is -3i squared. That's like -3 times -1. That's really a +3. Let's combine like terms. I get 24 for the real part and -2i for the imaginary part. And number 13, here we are taking a complex number and squaring it. That means we are multiplying it by itself. And again, we're going to FOIL. First, outside, inside, last is plus 9i squared. Negative 3 times negative 3 and I times I. Well, that's like 9 times negative 1. It's just a negative 9. If we combine like terms, I get a negative 5 and a negative 12i for that solution. Nice thing to remember here, you are going to have to show work. In other words, you're going to have to demonstrate how you're multiplying these together, but your calculator does have a feature that will allow you to look at or enter in an I term. Remember, that's like second decimal point, I believe. There is an I variable in your calculator that will do this work for you. It provides a very nice check. All right, the next section, solve the equation by finding square roots. For number 14, I just want to get to a point where I can square root both sides. I want to isolate this x squared. So let's add 2x squared to both sides. Then let's divide both sides by 2. And I get x squared equals negative 9. Now I can square root both sides. And since I am physically putting in that square root, I need to account for plus or minus. And hey, look at that. It's a negative under a square root. That's an imaginary number. So I can free that negative, treat that like a bluegill, and then square root of 9 actually comes out clean. This is x equals plus or minus 3i. We don't want to write I3. 3i is the proper way to express those pure imaginary numbers. We only put the I out front if it's got a radical left over like we did in 8 and 9. And for number 15, now this quantity is the thing that's squared. I want to isolate that so that I can undo that square with a square root. So I'm going to subtract 1 from both sides. I'm going to divide both sides by 3. Then I'm going to square root both sides. I square rooted both sides, so I need to remember a plus or minus is taking place there. And square root of 4 is simply 2. To finish solving for x, there's nothing happening around the parentheses, so that's really just x plus 5 there. I just need to subtract 5 from both sides. X equals negative 5 plus or minus 2. You will miss a half a point if you leave your answer that way. It is unsimplified. We have nice, clean, like terms that can be combined. We need to answer as the set of those two solutions. Negative 5 plus 2 would be negative 3. Negative 5 minus 2 would be negative 7. And we've gone over some other methods like the life hack in the calculator that can provide these answers for us. We're not going to see imaginary solutions show up in our calculator though, so we need to know how to do the pencil and paper mathematics. Okay, continuing on with our solving quadratics. Next we have completing the square. Remember, this is the only method where we want it not set equal to 0. We want to make a perfect place to establish a trinomial, and we mean filling in the blank. So I'm going to add 1 to both sides to establish that nice place where I can put in a number and cause a perfect square to happen. All right, well, what do I need to do? I take that middle term, that x term, and divide it by 2, and then square it. That tells me the perfect number to fill in the blank is a plus 1. And I brought in that plus 1 out of nowhere on the left side of the equation. I need to keep it balanced and add 1 to the other side as well. And then the whole point of completing the square is to be able to square root both sides. What perfect square trinomial have I made? Well, it's x, and then this negative 1 that I squared to fill in the blank. That's what makes this binomial being squared. And to wrap up the problem, we simply square root both sides. Again, we are physically square rooting, so we need plus or minus. Square root 2 doesn't simplify, so that's pretty easy to work with. And then lastly, we'll finish the problem by adding 1 to both sides. So 1 plus or minus root 2 represents my two solutions there. For number 17, this one has quite a bit to it. It's a tougher completing the square problem primarily because of this 2 that's out front. We cannot make a nice perfect square trinomial easily with that 2 being out front, so we're going to have to deal with that. It's already got the constant moved over to the other side. I just need to divide everything by 2 on both sides to get rid of that leading coefficient of 2. So I'll have x squared plus 3x, then I can fill in my blank, equaling 7 halves on the right-hand side. Well, what fills in the blank? I take that middle term and divide it by 2, and then square it. So I find that I'm adding 9/4 to both sides to keep that equation balanced and set up that perfect square trinomial. And I'm ready to get to the point where I have something squared. It's going to be an x and then a positive 3 halves inside that quantity. And on the right, I've got 7 halves plus 9/4. Man, I don't want to do decimals here. That would be a waste of time. 7 over 2 is the same thing as 14 over 4 if I establish a common denominator. This is 23 over 4 when I add those up. Then, to get rid of the square, we square root both sides. So I have x plus 3 halves equals, on the right, I square rooted that, so plus or minus, and then square root of the top is root 23, and the square root of the bottom, that's the square root of 4. That comes out nice and clean. It's a 2. And the last step is to subtract 3 halves from both sides, and because when I subtract that over, these both have a denominator of 2, I can combine them together as 3 plus or minus root 23 all over that common denominator of 2. There's our answer. Okay, and for our final method of solving quadratics, we have the quadratic formula, really just taking all of those steps of completing the square and kind of simplifying them for us, making a nice algorithm out of them that's easy for us to use. Sorry for bumping the microphone there. So let's get to it. We have this all set up in the proper order. We've got our x squared, our x, and then our constant set equal to 0. Well, quadratic formula, we should know this one now. X equals, our solutions equals opposite of b plus or minus the square root of b squared minus, I'm going to put this in parentheses, 4 times a times c all over 2 times a. That's 2 times 1 here. Well, let's simplify that radical. That's our first task. All those numbers are grouped together. I get 49 minus 52 underneath, and we can use a calculator to do this math for us. Just be sure that you're grouping this multiplication together, and we should get a nice answer of negative 3 all over 2. And really the only thing I can do to simplify this any further is account for the fact that my solutions are imaginary. So treat that radical like a bluegill, negative 7 plus or minus I root 3, all that over 2. We cannot simplify that radical any further. That question is done. Final problem number 19, I need to get it set equal to 0 since we're using quadratic formula. So I will add 9x squared to both sides. Make sure that it's in the proper form before I start determining what a, b, and c are. Well, let's use our quadratic formula now. It's in the right order. Opposite of b plus or minus the square root of b squared. Negative 2 squared is going to be a positive 4. Be very careful when you use a calculator here. If you're getting negative 4 or a negative number anytime you use quadratic formula at the start, you're doing something wrong. If we square a negative number, it becomes positive. A lot of students make very ignorant mistakes there by maybe working too quickly. So we have b squared minus 4 times a times c all over 2 times a. That's going to be 18 here. Let's simplify the radical. I got 4 minus 144, so that's negative 140. And we could use a calculator to do that quick arithmetic there. That would be a good use of the calculator. And we do have an imaginary term here. And I have my suspicions about that root 140, so maybe I'll break off and factor tree that. Hey, we can free a 2, but not that 35. That's just a 5 and a 7. None of those have perfect pairs, so that's left underneath our radical. So 2i root 35 is where we're at, all over 18. And we can simplify this by dividing all the pieces there, that both parts of our numerator and the denominator, they're all divisible by 2. So I get x equals 1 plus or minus 1i root 35 all over 9 as a simplified answer. All right, we made it through the tough part. um, Here's where the test eases up a little bit. I definitely see that being the crucial point to get through on the test is all those different solving problems. Next, we have solve the system of nonlinear equations, and we can use substitution or elimination here. I prefer the substitution method myself when it's available, um, but you're more than welcome to use elimination as well. For number 20, substitution seems to be our only bet. If I take this negative 3 plus x and substitute that in for y, then I'll have an equation that only has x's in it. So I've got x squared plus not y, but negative 3 plus x being squared, and that's equal to 9. Let's FOIL out all of this. So I got x squared plus, I've got positive 9 minus 6x plus x squared. And let's get that set equal to 0. I've got 2x squared and negative 6x when I combine like terms. And I'm going to subtract 9 from both sides to try and get it set equal to 0. So it equals 0. I can factor this very easily with a GCF and find that x equals either 0 or 3. That means my solution points are 0 comma something and 3 comma something. And let's plug those into this nice second equation to find the y values that go with them. If I plug in a 0, y equals negative 3 plus 0. It's just negative 3. If I plug in an x value of 3, y equals negative 3 plus 3. Oh, that's 0. So those are my two solution points for that one. For number 21, again, this is one where you could go through and use the elimination method here and eliminate the y's. But if these are both set equal to y, I'm going to take all of this and just quickly substitute it in here. So it kind of looks like a mess early on, but we can combine like terms very quickly. It will do the same thing that elimination method does with combining like terms. So x squared minus 3x plus 22 equals 2x squared minus 5x plus 7. And let's go ahead and combine our like terms. I'm going to subtract over x squared. I can see that I've got x squareds and x's and constants, so I know I've got a quadratic forming, and that should be no surprise. Again, we are working with quadratic equations here, so I'm going to subtract away everything from the left and combine it with what's on the right. So if I subtract away x squared from both sides, I'll have 1x squared on the right. If I add 3x to both sides, I will have minus 2x. And if I subtract 22 from both sides, I will get negative 15. And this is a nice quadratic that factors very, very quickly. So x minus 5, x plus 3 equals 0. I can quickly find by factoring that x equals 5 and negative 3. So I've got 5 something and negative 3 something. And it's a little bit more work to plug them back in, but this original equation, it's not terrible. If I plug in a 5, 5 squared is 25, minus 3 times 5, that's 15, plus 22, I get 32. And again, the calculator can help with some of this quick arithmetic. We just want to be careful with negatives. If I plug in a negative 3, 2 times negative 3 squared. Well, negative 3 squared is positive 9, so that first term's an 18. And then negative 5 times negative 3 is positive 15, and then plus 7. So I get 33 plus 7, 40. Those should be my two solution points. And you'll see we haven't touched the calculator yet. This is something that if we just know our concepts, the numbers are very manageable. As long as we don't stall out on any problem, we're going to be in really, really good shape. Okay, let me move my recording window here. Solve the inequality algebraically and graph our solution on a number line. Well, our first task, and you can see that this number 22 has already been set up very nicely for us in this regard, is to compare it to 0. So I'm saying, where does this quadratic have a height that is less than or equal to 0? Well, on my number line, I'm going to need a couple key points, and that's where it actually equals 0, because what we've got is an upward-facing parabola, and at certain places it will have heights above the x-axis, it will have heights that are greater, and at certain places it will have heights that are lower. So I need to find those 2 points. That's what's going to go on my number line. Thankfully, this one is very easy to factor. I'm just going to treat it as if it were an uh, quadratic equation right now instead of an inequality, and I find that those key points are x equals +4 and -2. So I'll plot those points on the number line like so. And because this parabola is opening upward, I know its height will be less than 0 between those 2 points. Okay, but I want to be 100% certain. I've got a really good idea that that's what's going to happen. Using this symbol, less than or equal to, I know that the points are going to be solid because I include those points on the axis where the height equals 0. That's allowed. And then I'm just going to test the point 0. So 0 on my number line would fall right there. I'm going to test that in the original equation and see if it's true or not. If it's true, then I will do my shading there. If it's not, then I'll do my shading on the outside. If I plug in a 0, 0 squared is 0, minus 2 times 0, 0, minus 8. Is that total less than or equal to 0? Yes, it is. So my solution set is all values of x in between those. 0 worked, so that's where I shade. For number 23, here we've got a little bit of setup. X squared, let's add the 3x to both sides, and then minus 4. Set that up so it's compared to 0. Another easy one to factor, I've got +4 and -1 for my magic numbers. So on the number line, I'm plotting a -4 and a +1. All right, now let's think of what's happening here again. Yet again, we have a upward facing parabola crossing the axis at a couple points, and I want to know where its height is above. I'm thinking that my shading is going to happen outside because when I have those 2 points, the height is higher than the x-axis off on either side, off to the left and off to the right. So let's plot our points on the number line based on the inequality symbol. It's strictly greater than, so it will have open circles there. And then again, let's test 0. 0 is in the middle, so I'm going to test that in the original inequality. If it works, that's where I'll shade. If it doesn't work, I'll shade on the opposite sides. So let's take a look. If I plug in a 0, I get 0 squared minus 4 is greater than -3 times 0. Well, -4 is not greater than 0, so that does not work for a solution set. It didn't work inside, so my solutions are outside. Okay, 24, now we're looking at quadratic inequalities that have x's and y's involved, so we're not just looking at the number line anymore, but now we're looking at shaded regions that are either inside or outside the parabola. So as I look at these equations, the first one, I'll graph that one in green. I notice that based on the inequality symbol, it's less than or equal to. Well, that or equal to means it's a solid graph. And because it's less than or equal to, I know I'm going to shade below that graph once I make it. And to make the graph, just like in the first part here, we could use our calculator and find a table of values, or we could use x equals -b over 2a and use our standard parabolic growth. So -b over 2 times a equals a +3 for my axis of symmetry for that first parabola. And if I plug in a 3, I get -3 squared plus 6 times 3 minus 1. I get a value of +8. So at +8, that's where my vertex is for that parabola. And I know it's opening downward. It's a -x squared. So I'll use my standard parabolic growth to chart that out. And I believe it'd be here, right? And I know this was going to be a solid graph, and my shading is below that graph, so at any point on that graph, I know the shading will happen underneath. And I'll just show that with some arrows. The only thing I really want to shade is my solution set. For the second equation, we'll shade that one in blue. It's a greater than inequality, so I know that means it's a dashed graph. doesn't include the parabola itself, and I'm shading above because my y values, my heights, are greater than the function. And again, let's use x equals negative b over 2 times a. I get negative 2.
Attention staff, the 8 o'clock training sessions are about to begin for Haiku and Mastery Manager 101. If you have not signed up yet, you are still welcome to attend. Again, 8 o'clock training sessions are about to begin.
Apologize for that little interruption. We will wrap up this problem and then I can get to the training I'm supposed to go to. So we draw in our axis of symmetry there. We plug in our negative 2 into that equation. I get a positive 4 minus 8 minus 5. Well, that's negative 9. Plot that point and use my standard parabolic growth again to graph that very, very quickly. And we said this was a dashed graph. And we are going to be shading above that graph. So for my actual solution, what is the region that is shared by both of those inequalities? It's this little sliver here where those graphs overlap. So that is my solution. I want to make sure that that is clearly shown, that that is the solution to that system of quadratic inequalities. Again, remember that we could have graphed this using a table of values for each of our parabolas, but we would have still had to know how to shade appropriately and everything. So this one made a lot faster, I think, without the calculator, but we do have that check in place. All right, and we come into the final questions on this review. A couple of word problems involving situations that are modeled by quadratic functions. Parker is painting a 2-story house. He drops his paintbrush from a height of 20 feet. How long does it take for the paintbrush to hit the ground? Round your answer to the nearest 100th place. Well, what we're going to do here is we're going to find out where that paintbrush, when it hits the ground, it's going to have 0 height. So this function, and it's not really very clearly labeled. It should say h of t if it were better written, equals negative 16t squared plus 20. That way we know that the height given a time is found by this equation. So if we want our height to be 0, when it hits the ground, then we can solve that for the t, right? The question is saying how long, so we're going to solve for the time there. And here, very easy to solve. We just subtract 20 from both sides, divide both sides by negative 16, and then square root both sides. Now, when we square root, we are taking that plus or minus into account. Square root of the top is root 5. Square root of the bottom is just a 2. However, that, oh, sorry, I did some extra work there on my own. We divided by, no, I didn't. No, that's good. So now what we actually have to do is just calculate this and realize that he didn't drop the paintbrush some time ago. So we're only looking at the positive instance here for time if we're going to answer that question. So if I take the square root of 5 and divide it by 2, I will get my answer. And here, I don't have any fancy tricks or anything to do in the calculator. We just simply type in square root of 5 and divide it by 2. And I get 1.12 seconds. Of course, rounding to the 100th place, the actual answer on my calculator was 1.11803 and so on, but the 100th place, I'm looking at what follows that second 1, and since it's an 8, I would round that up. I know it seems kind of trivial to bring that up in Algebra 2, but I do have plenty of students that come through and don't round accordingly. And that can be something that can actually hurt you on things like the SAT and so forth. And lastly, number 26, a water balloon is tossed into the air so that its height, h in feet, after t seconds can be modeled by this function. That one's written a little bit better with h of t. What is the height of the ball after 2 seconds? Well, should say balloon. After 2 seconds, when does the water balloon hit the ground? So we've got 2 things that we need to calculate here. The first one's pretty easy. What is the height after 2 seconds? Well, we have a time for an input. We want the height for an output. That's how the function's designed to work. So to answer that first part, h of 2 equals negative 16 times 2 squared plus 80 times 2 plus 5, negative 64 plus 160 plus 5 equals 101 feet. And yet again, calculator can help with some of that arithmetic. It's the second part where we can really use the calculator to help out. So I want to find out when it hits the ground. So again, now I'm trying to answer for t, a time. I want to know when that height is 0. And it's not impossible to do this one. We might want to see if it's factorable or something like that first. But yikes, finding a 0 out of this is going to be an awful lot of work. We could use quadratic formula with it. That's an awful lot of work as well. So what I would like to do is graph that and let the calculator do the heavy lifting. Very, very nice to do that with a problem such as this. So let me bring up my calculator here. There we go. And after turning the calculator on, we'll go to y equals and we will type in negative 16. We have to use x as an input variable. Squared plus 80x and then plus 5. And that's good. And then I'm going to look at the graph, and you can see it's a pretty steep parabola as time's going by, and there is a maximum point up there. So I may zoom out on that, and you can see that's not really helping my view very much. But even if I had my standard zoom that I started with, I know the graph is peaking up here. I know it's a negatively opening parabola, so I can do a calculate maximum. So second trace opens up the calculate menu, and a maximum is option 4. Go from my left bound to my right bound. I'm just going to toggle to the right. I see it climbing up and climbing down. You can see that when we trace our point right around x equals 2, we get a height that 101 seems pretty good right now. So I'm just going to hit enter and enter. I'm just watching the y values to see when they peak and start to come back down. It's going to scan in between, and then it will tell me that the maximum happens 2.5 seconds in, meaning that this was in fact factorable, and that height is 105. But wait a second, I wasn't trying to find the maximum height that it reaches. I did this completely wrong. I'm trying to find out when does it come back down and hit the ground. So I want to calculate this 0. So I'll go back to my calculate menu, choose the 0 option, and I'm just going to toggle to the right until I get close to that 0. Make sure I'm to the left of it, hit enter to start scanning, move until I'm past it to the right, hit enter again to stop scanning, and it says at 5.06. That's when I have my my 0 there, so 5.06. And if you'll notice, I did make a little claim there that I used Calc 0. So when you're doing this type of work, it's really nice for me as the teacher to see how you're arriving at that answer. I don't want to see just an answer written down. So here by saying via Calc 0, I know you're using your calculator, and I know you're using the 0 function in that calculator to come up with your answer. You could have used quadratic formula there, like I said, and it looks like since we got 5.06 is actually not factorable. Although our axis of symmetry came out nice even at that 2.5, our zeros did not. But yeah, we're more than welcome to use Calc 0. If you used the quadratic formula program we wrote in our calculators, you could say via Calc quad form or something like that. That would also suffice as an answer. So there you have it. That's the end of this Chapter 3 review. Again, hope we're being very diligent in asking good questions and making sure that we are understanding everything that goes with solving quadratics, because as we move further on into the year, we're going to look at different types of functions, and a lot of the concepts we're covering here apply there as well. So happy studying and good luck on this test.